Hey, before we get into anything, I want you to do something for me. Just look at your hand for a second. Go ahead, I'll wait. No, seriously, actually look at it. See the skin, veins, maybe a scar or two from some accident you barely remember. Every single atom in that hand, every last one, has a history. And that history doesn't start when you were born. It doesn't start with your parents or their parents, or even with the first humans who ever walked on this planet. It starts in space. It starts inside a star. A star that was born, lived for millions, sometimes billions of years, and then exploded in one of the most violent events the universe is capable of producing. And in that explosion, the atoms that would eventually become you were scattered across the galaxy. They drifted through cold, dark space for millions more years. Then they got pulled together into our solar system, into our planet, into the oceans, into the first living cells, and eventually, after an almost incomprehensible chain of events, into you, sitting here, watching this video, looking at your hand. I'm not saying that to be poetic. I'm saying that because it is literally, chemically, physically true. And once you understand the full story, the real story of how stars are born, how they live, how they die, and what they leave behind, you will never look up at the night sky the same way again. I promise you that. So, you ready? Let's go. The nursery where stars are born. Okay, so, stars. We see them every night. Well, most of us could see them every night if we weren't surrounded by so much light pollution, but we'll get to that. And they just look like dots. Static, fixed, permanent. But here's the thing. Nothing about a star is static. Nothing about a star is fixed. And they are definitely not permanent. Stars are alive in a sense. Not biologically alive, obviously, but they are born, they grow, they change, they age, and they die. And the story of how a star is born might be the most dramatic origin story in the entire universe. It starts with nothing. Or not quite nothing. It starts with almost nothing. The nebula, space's most beautiful mess. Picture this. You're floating in deep space, way out, far from any star, far from any planet. It's cold, like incomprehensibly cold. We're talking temperatures close to absolute zero, around minus 270 degrees Celsius. That's so cold that most atoms barely move at all. And all around you is this enormous, thin, wispy cloud of gas and dust. Mostly hydrogen, a little bit of helium, tiny traces of other elements, carbon, oxygen, nitrogen. This cloud is called a nebula, and it might be hundreds of light years across. A light year, just to be clear, is the distance light travels in 1 year, and light travels at 300,000 kilometers per second. So, 1 light year is roughly 9.5 trillion kilometers. And this nebula, it could be hundreds of those across. It looks from a distance, if you could somehow see it, absolutely stunning. These clouds of gas glow in colors that look almost painted. Pinks and purples and deep blues and electric greens, lit up by nearby stars. The Hubble Space Telescope has given us images of nebulae that honestly look more like art than science. But up close, it's just cold, dark, sparse gas. Almost nothing. So how does that become a star? The trigger. Something has to start the fire. Here's where it gets interesting. That cloud of gas is just floating there, minding its own business, and left to its own devices, it might just keep floating there forever. But something has to disturb it. Something has to give it a push. And in most cases, that push comes from one of the most violent events in the universe, another star dying. When a massive star reaches the end of its life, it explodes in a supernova. We'll talk about supernovae in extensive detail later, and trust me, you want to stay for that part. But for now, just know this. A supernova sends out a shock wave, a literal pressure wave rippling through space at thousands of kilometers per second. And when that shock wave hits a nearby nebula, a nearby cloud of cold gas, it compresses it, it squeezes it. And here's the beautiful part. Once you start squeezing a cloud of gas, gravity takes over. Because every single particle in that cloud has mass, and every particle with mass has gravity. It's weak, almost unimaginably weak for a single hydrogen atom, but it's there. And when you compress the cloud, the particles get closer together, and when they get closer together, their collective gravity gets stronger. And a stronger gravity pulls more gas inward, which compresses it more, which increases the gravity further, which pulls more gas in, and on and on and on. This process is called gravitational collapse, and once it starts, it doesn't stop. The cloud begins to pull itself together, very, very slowly at first. We're talking about a process that can take millions of years to even begin to show results. Millions. Years. I want you to really sit with that for a second. The formation of a single star can take longer than the entire history of complex life on Earth. The protostar, a star in progress. As the gas cloud collapses inward, something interesting starts happening at the center. The gas is getting denser, and denser gas means more collisions between atoms, and more collisions means more energy, and more energy means heat. The center of this collapsing cloud starts to get warm, then warmer, then hot, then very hot. As more and more material falls inward, pulled by gravity, the central region, which astronomers call the core, gets hotter and hotter and hotter. At this stage, we're no longer looking at a nebula. We're looking at a protostar. A protostar is basically a star in progress. It's a dense, hot, glowing ball of gas that hasn't quite figured itself out yet. It's still surrounded by a swirling disk of gas and dust, the material that hasn't fallen into the core yet. This disk is actually really important because it's where planets will eventually form. But we'll get to that whole story another time. The protostar is also, and I love this detail, not very bright in visible light. Because it's surrounded by all that gas and dust, which absorbs and blocks the light. But in infrared, in heat radiation, it blazes. NASA's James Webb Space Telescope, which if you haven't looked up images from it yet, please do that immediately after this video, can actually see protostars that are completely invisible to optical telescopes because it observes in infrared. And what it's found is extraordinary. Protostars hidden deep inside nebulae, just beginning to ignite. Starbirth, happening right now in real time. The ignition, when everything changes. So, the protostar is getting hotter and hotter. The core is being compressed more and more by the weight of all the material above it. And at some point, after maybe 100,000 years, sometimes several million years, the core temperature hits a critical threshold. About 10 million degrees Celsius. 10 million degrees. And at that temperature, something happens that changes everything. Nuclear fusion begins. Now, I want to explain what nuclear fusion actually is, because it's one of those phrases that gets thrown around a lot without anyone really explaining what it means. At its most basic level, nuclear fusion is when two atomic nuclei, the centers of atoms, get slammed together so hard at such extreme temperatures and pressures that they merge into a new, heavier atom. In the case of a young star, the fusion happening is the simplest kind, hydrogen fusion. Two hydrogen nuclei, which are just single protons, get smashed together to eventually form a helium nucleus. And here's the key thing. A helium nucleus weighs slightly less than the two hydrogen nuclei that formed it. That missing mass, a tiny, tiny amount, doesn't disappear. It gets converted into energy. And this is Einstein's famous equation, E equals mc squared. Energy equals mass times the speed of light squared. The speed of light is 300,000 kilometers per second squared. That's 90 quadrillion. 90 quadrillion. So even a tiny amount of mass, when you multiply it by 90 quadrillion, produces an enormous amount of energy. And this is what stars do every second for billions of years. The balance, the most important relationship in the universe. So now we have a protostar that started nuclear fusion. And here's where something almost philosophical happens. Because now we have two forces fighting each other. On one side, gravity. Gravity is constantly trying to pull all the star's material inward. It wants to collapse the star. It wants to squeeze it down to nothing. Gravity is relentless, patient, and never, ever stops. On the other side, radiation pressure. The energy released by nuclear fusion, all those photons, all that heat, pushes outward. It's an explosive force radiating from the core. And a stable star is a star where these two forces are perfectly balanced. Gravity pulling in, radiation pressure pushing out, neither one winning. This balance has a name. It's called hydrostatic equilibrium, and it's one of the most elegant things in nature. A star is essentially a constant, ongoing negotiation between the force that wants to destroy it by collapsing it and the force that wants to explode it by exploding it. And for billions of years, billions, that negotiation holds. The star just sits there, burning, glowing, stable. We call this the main sequence, the long, stable adult phase of a star's life. Our sun has been in this phase for about 4.6 billion years, and it'll stay there for about another 5 billion. But here's the thing. That fuel, that hydrogen in the core, it's not infinite. Every second, the sun fuses about 600 million tons of hydrogen into helium. Every single second. That sounds like a lot, and it is. It's a mind-bending amount of material. But the sun weighs about 2 octillion tons. That's a 2 followed by 27 zeros. So it has fuel to burn for a very long time, but not forever. And what happens when a star starts running out of fuel? That's where the story gets really interesting. But before we get to there, we need to talk about something that most people don't realize. Not all stars are the same. And the difference between a small star and a massive star is the difference between a quiet retirement and a violent, catastrophic death that reshapes the entire galaxy. Stay with me. The variety. Not all stars are created equal. When you look up at the night sky, all the stars kind of look the same, right? Little white dots. Maybe a few that are slightly different colors if you look carefully. But the reality is that stars come in an absolutely staggering range of sizes, temperatures, brightnesses, and colors. And the single most important factor in a star's entire life, the thing that determines almost everything about it, is its mass. How much stuff it's made of, how heavy it is. The smallest stars, called red dwarfs, are maybe 8 to 50% the mass of our sun. They're small, cool, and dim. They burn their hydrogen so slowly, so efficiently, that they can live for trillions of years. Trillions. To put that in perspective, the universe is only about 13.8 billion years old. A red dwarf star that formed in the early universe is still in the beginning of its life. No red dwarf star has ever died yet because the universe isn't old enough for that to have happened. We know they'll eventually die, the math tells us that, but we've never actually observed one completing its full life cycle. We probably never will. Then there's our sun. Our sun is a yellow dwarf, a medium-sized, middle-of-the-road kind of star, nothing too extreme. It'll live for about 10 billion years total, perfectly average in cosmic terms, which is actually a good thing, because extreme stars have extreme fates. Then there are the giants, stars that are 8, 10, 20, 50, even 100 times the mass of our sun. These stars burn hard. They fuse hydrogen at a ferocious rate. They're blazing hot, blue-white in color, almost blindingly bright. And because they burn so fast, they burn out fast. A star with 10 times the sun's mass might live for only 20 or 30 million years, which sounds like a lot, but in cosmic terms, it's practically a blink. And when these stars die, nothing in the universe is more violent. We'll get to that. But first, let me tell you about the long, surprisingly calm middle part of a star's life, because there's actually a lot going on inside a stable star that most people never think about. Okay, so we've got a star. It's formed, it's stable, fusion is happening in the core, hydrostatic equilibrium is doing its thing, and from the outside, from billions of miles away, it looks peaceful. Just this glowing, steady ball of light. But inside is chaos. The core, a nuclear reactor the size of a planet. Let's take an imaginary journey into the sun. Not literally, obviously. The surface of the sun is about 5,500 degrees Celsius, which is already more than hot enough to instantly vaporize anything we know of. But the core? The core of the sun is about 15 million degrees Celsius, and it's under pressure so extreme that, and this comparison genuinely makes my head hurt, the pressure at the sun's core is about 250 billion times the atmospheric pressure at Earth's surface. 250 billion times. At these conditions, hydrogen nuclei, protons, are slamming into each other constantly. Now here's something most people don't realize. Not every collision results in fusion. In fact, the vast majority of collisions don't. Protons are positively charged, and like charges repel each other. So two protons slamming together at almost any speed would just bounce off. For fusion to happen, the protons need to get close enough, incredibly close, for a different force to kick in. That force is the strong nuclear force. And the strong nuclear force is, true to its name, incredibly strong. It's about 137 times stronger than electromagnetism at close range. But, and this is key, it only works at extremely short distances. We're talking about distances smaller than an atomic nucleus itself. So for fusion to work, two protons need to somehow overcome their electromagnetic repulsion and get close enough for the strong nuclear force to grab them. At normal temperatures and pressures, this would be essentially impossible. But at 15 million degrees and under that incomprehensible pressure, quantum mechanics does something remarkable. Quantum tunneling. This is one of my favorite concepts in all of physics, and I'll try to do it justice. At the quantum scale, the scale of individual particles, particles don't have perfectly defined positions. They exist in probability distributions. There's a small but non-zero chance that a particle is in a slightly different place than you'd expect. And this means that two protons that, by classical physics, should not be able to overcome the electromagnetic repulsion barrier between them, occasionally just appear on the other side of it. They tunnel through. They quantum tunnel through the barrier, find themselves close enough for the strong nuclear force to act, and fusion occurs. It's genuinely bizarre. Quantum mechanics says the rules you think are solid, they're more like suggestions, and occasionally, at the very small scale, particles break them. And stars rely on this. If quantum tunneling didn't exist, nuclear fusion wouldn't happen at the temperatures inside stars. The sun would never ignite. There would be no stars. There would be no universe as we know it. Quantum weirdness isn't just a laboratory curiosity. It is literally the reason you're alive. The journey of light, the slowest, fast thing. Here's something that genuinely messed with my head when I first learned it. Light, which travels at 300,000 kilometers per second, is the fastest thing in the universe. It takes light about 8 minutes to travel from the sun to Earth. So the light hitting your face on a sunny day left the sun 8 minutes ago. Pretty fast, right? Now here's the question. How long did it take that light to get from the center of the sun to the surface of the sun? 8 minutes? Less? Nope. Somewhere between 10,000 and 170,000 years. I'm serious. Here's why. Light doesn't travel from the core of the sun to the surface in a straight line. It can't. The interior of the sun is so dense, packed with so many particles, that a photon of light gets absorbed almost immediately after it's created. It gets absorbed by a particle, heats that particle up slightly, and then gets re-emitted in a random direction. And then it gets absorbed again and re-emitted again in another random direction, over and over and over. This process is called a random walk, and because every step is random, equally likely to go in any direction, progress from the core to the surface is agonizingly slow. The photon stumbles around, bouncing off particles for tens of thousands of years. Eventually, randomly, it works its way out to the surface, and then it screams across 150 million kilometers of empty space in just 8 minutes. The sunlight warming your skin right now started its journey to you somewhere between 10,000 and 170,000 years ago.
back when early humans were just beginning to develop complex art and culture on Earth. That light was already beginning its slow, stumbling journey toward you. Think about that next time you're sitting in the sun.
Stellar neighborhoods, the galaxy as an ecosystem. Here's something else I want you to think about. Our galaxy, the Milky Way, contains somewhere between 100 and 400 billion stars. All of these stars are going through their own life cycles. Some are just being born in stellar nurseries right now. Some are in the middle of their long, stable main sequence lives. Some are aging, expanding, changing. Some are dying, and some have already died, leaving behind the strange, exotic remnants we'll talk about in detail soon. The galaxy is essentially an ecosystem. Stars are born from nebulae. They live their lives fusing hydrogen into helium, helium into heavier elements, and when they die, especially when they die violently, they enrich the gas around them with all those heavier elements they've spent their lives creating. That enriched gas eventually becomes the next generation of nebulae, and from those nebulae, new stars form. Stars that are richer in heavy elements than the stars that came before. Because each generation of stars creates new elements, scatters them into space, and seeds the next generation. The first stars that ever formed in the early universe, just a few 100 million years after the Big Bang, were made of almost nothing but hydrogen and helium. No carbon, no oxygen, no iron, no silicon, no possibility of rocky planets, no chemistry complex enough for life. Our sun is what astronomers call a third-generation star, or possibly even later generation, which means the gas cloud that formed our solar system was already enriched by the deaths of at least 2 previous generations of stars. All those carbon atoms in our bodies, all the oxygen we breathe, all the iron in our blood, all of it was made by stars that lived and died before our sun was even born. We didn't just happen to show up in a universe with stars in it. We are downstream from stars. We are made of them. And now we're getting to the part of the story where it gets darker, literally and figuratively, because we need to talk about what happens when the fuel starts to run out. The identity crisis, when stars start to change. All right. A star has been happily fusing hydrogen in its core for billions of years. In our sun's case, 4.6 billion years and counting. Hydrostatic equilibrium has been holding. Gravity and radiation pressure in perfect balance. Life has been good. But nothing lasts forever, and here's where the story takes a turn. The hydrogen problem. Remember, stars fuse hydrogen into helium. But here's the thing, that helium, it doesn't disappear, it builds up. Every fusion reaction in the core takes hydrogen and produces helium, and the helium just accumulates in the center of the core. Now, at the temperatures inside a main sequence star like our sun, helium cannot fuse. It needs temperatures much higher than that to undergo its own fusion reactions. So the helium just sits there, inert. And as it accumulates, it starts taking up space in the core. And as it takes up more space, there's less and less hydrogen left to fuse. The fusion rate starts to drop. And here's where the balance starts to shift. If the fusion rate drops, that means less energy is being produced, less radiation pressure pushing outward. But gravity doesn't care. Gravity's always there, always pulling inward. So what happens? The core contracts. Gravity wins just a little. The core squeezes inward just slightly. And when you compress gas, it heats up. Remember we talked about this. Compression equals heat. So the core gets hotter. Now here's the twist. This increased temperature doesn't reignite helium fusion. Not yet. It's still not hot enough for that. But it does something else. It ignites a thin shell of hydrogen surrounding the core. Hydrogen that was previously too far from the high-pressure core to be fusing. Now it starts fusing too.
And this shell fusion produces energy. More energy, actually, than the core was producing before. And all that extra energy, all that extra radiation pressure does something dramatic. The expansion, going through changes. All that extra energy pushes outward on the outer layers of the star. Remember, the outer layers of a star are just gas. They're not solid. They can be pushed. And so the outer layers start to expand, slowly at first, then faster. The star starts to swell. As the outer layers expand outward, they cool down. Hotter gas, when it expands, loses heat. This is basic thermodynamics. So as the star expands, its surface gets cooler. And a cooler surface means a different color. You might know that hot things glow blue and cooler things glow red. It's the same principle as a metal rod you heat in a fire. It goes from black to dull red to bright orange to yellow-white as it gets hotter. Stars work the same way. As our sun expands and its surface cools, it will shift in color from the yellow-white it is now towards orange and eventually towards red. And it won't just change color. It will grow enormously. Our sun in its current state is about 1.4 million kilometers in diameter. By the time it's finished expanding, it will be somewhere between 100 and 200 times that size. We call this a red giant. A red giant. And when our sun becomes a red giant in about 5 to 7 billion years, its outer edge will expand to roughly where Earth is now, possibly beyond Earth's current orbit. Now, whether Earth survives this is actually a somewhat complicated question. As the sun expands, it will also be losing mass, blowing material off its outer layers in a much more intense version of the solar wind. As the sun loses mass, its gravitational pull decreases, and as the gravitational pull decreases, Earth's orbit might expand outward, staying just ahead of the expanding sun. Some models say Earth survives. Others say it gets engulfed. Either way, the oceans will have long since evaporated, the atmosphere will have been stripped away, and Earth's surface will be a scorched, dead rock. Possibly a scorched, dead rock that gets swallowed by a dying star. Not exactly a comforting thought, but also 5 to 7 billion years from now, we have some time to figure it out.
Solar wind and the star's personality. Okay, so we've established that inside a star is chaos. But even on the outside, the surface of a star, things are wild. The surface of our sun isn't a solid surface. There's no ground there. It's a constantly churning, boiling, churning sea of plasma, gas so hot that electrons have been stripped from their atoms entirely. And from this surface, the sun is constantly breathing out particles. We call this the solar wind. The solar wind is a stream of charged particles, mostly protons and electrons, that flows out from the sun in all directions at about 400 kilometers per second. This solar wind actually reaches Earth. When solar wind particles hit Earth's magnetic field, they get funneled toward the poles and slam into our upper atmosphere. The energy from these collisions excites oxygen and nitrogen molecules, and they release that energy as light. The aurora borealis. The northern lights. One of the most beautiful sights on Earth is literally caused by the sun sneezing in our direction. I love that. But here's the thing. The solar wind isn't constant. The sun has storms, solar flares, massive bursts of radiation and energy from the sun's surface, coronal mass ejections, enormous bubbles of plasma and magnetic field that get hurled into space. When a really big coronal mass ejection hits Earth, the aurora can be visible much further south than usual. In 1859, the largest solar storm ever recorded, called the Carrington event, was so powerful that telegraph machines across North America and Europe caught fire. The aurora was seen as far south as Cuba and Hawaii. If a Carrington-level event hit Earth today, with our modern dependence on electronics and satellites, some estimates suggest it could cause trillions of dollars in damage and knock out power grids across entire continents for months. So yeah, stars have personality, and our sun is in its calm, middle-aged phase right now. It wasn't always this calm, and it won't stay this way forever. The Sun's history, a life examined. Our Sun formed about 4.6 billion years ago from a cloud of gas and dust that was itself the remnant of older dead stars. In its early life, it was actually dimmer than it is today, by 30%, which creates a really interesting problem in Earth's history. If the early Sun was 30% dimmer, Earth should have been frozen solid. The math says so. At that reduced solar output, our planet should have been a giant snowball. But the geological evidence, the rock record, shows that liquid water existed on Earth almost from the very beginning. How? This is called the faint young sun paradox, and scientists are still debating it. The leading theories involve a much thicker atmosphere with more greenhouse gases, carbon dioxide, methane, that trapped enough heat to keep the oceans liquid despite the weaker sunlight. Early Earth's atmosphere was very different from today's. No free oxygen, lots of carbon dioxide and methane. And life, early microbial life, actually changed that atmosphere over billions of years. The Great Oxidation Event, about 2.4 billion years ago, was when cyanobacteria, photosynthetic bacteria, had been pumping oxygen into the atmosphere for so long that it finally reached significant concentrations. And that oxygen was toxic to most life at the time. One of the most impactful extinction events in Earth's history was caused by breathing, by life changing the planet's atmosphere by doing what it does. By, in a very real sense, the Sun interacting with life on Earth to reshape what Earth is. We are so entangled with our star. And our Sun has been changing too, slowly getting brighter as it ages. In about 1 to 2 billion years, it'll be bright enough that Earth's oceans will start to evaporate. Not because of anything we do, just because our Sun is getting older. The stellar spectrum, stars across the universe. While we're in the stable life phase of the story, let me tell you something that I find genuinely beautiful about how we know anything about stars at all. Stars are, to put it mildly, very far away. The nearest star to our Sun, Proxima Centauri, is about 4.24 light-years away. At the fastest speed any human spacecraft has ever traveled, about 70,000 kilometers per hour, it would take us roughly 37,000 years to get there. We cannot visit stars. We cannot send probes to them. We cannot take samples. All we can do is look at their light. And yet, from just that light, we can tell extraordinary things about them. We can figure out a star's temperature. We can figure out its chemical composition. We can figure out whether it's moving toward us or away from us, and how fast. We can figure out its age. We can even figure out whether it has planets. How? The answer is spectroscopy. When starlight passes through a prism, or a diffraction grating, the modern equivalent, it spreads out into a rainbow spectrum. But it's not a perfect rainbow. There are dark lines in it, specific wavelengths where the light is absent. These are called absorption lines, and they're caused by atoms in the star's atmosphere absorbing specific frequencies of light. And here's the beautiful part. Every element absorbs a unique, specific set of wavelengths. Hydrogen has one pattern. Helium has another. Iron, calcium, sodium, each one has its own fingerprint in the spectrum. So by looking at the dark lines in a star's spectrum, we can read its chemical composition like a barcode. We can look at a star 1,000 light-years away and know exactly what it's made of, from here, without going anywhere near it. The entire field of astrophysics is built on this one remarkable fact. Light carries information, and we've gotten remarkably good at reading it. The red giant phase. A star having a midlife crisis. Okay, I said this earlier, and I want to come back to it. Stars in the red giant phase are genuinely going through something. The analogy I keep coming back to is a midlife crisis. They've been doing the same thing for billions of years, quietly, efficiently fusing hydrogen, happy in their equilibrium, and then, suddenly, the fuel situation changes. They have to adapt. They start changing their appearance dramatically. They start consuming things around them. When our sun becomes a red giant, it will expand so much that it will swallow Mercury and Venus and possibly Earth. So yeah, dramatic transformation, consuming everything close to them, completely changed appearance. Red giant equals cosmic midlife crisis. But it's also beautiful in a strange way, because from a distance, from the perspective of some hypothetical observer in another star system, our sun in its red giant phase would be one of the most spectacular objects in the sky. Giant, glowing red, surrounded by a halo of gas being blown off its surface. Stunning. Anyway, so we've got this red giant, the core is still contracting, getting hotter, and all that helium that's been building up in the center is about to become very relevant. The helium flash, the most violent moment you've never heard of. Here's something that sounds like science fiction but is completely real. As the red giant's core contracts and heats up, it eventually, after millions of years of the red giant phase, hits a temperature of about 100 million degrees Celsius. That's 100 million, 10 times hotter than the core of the sun right now. And at 100 million degrees, helium can fuse. Helium nuclei, which have 2 protons and 2 neutrons, can now smash together to form carbon. And carbon can react with another helium nucleus to form oxygen. So now the core is fusing helium into carbon and oxygen. This is called helium burning. Even though there's no actual burning involved, it's still nuclear fusion. But here's the thing. For a star like our sun, this transition doesn't happen gradually. It happens in an explosion. Because the helium in the core has been compressed so much that it's become what physicists call a degenerate gas. A degenerate gas doesn't behave like normal gas. Normal gas, when you heat it, expands. This expansion cools it down, which reduces the fusion rate, which acts as a natural thermostat. A degenerate gas, when you heat it, does not expand. The pressure it exerts is essentially independent of its temperature. So, when helium fusion begins in the degenerate core, the heat produced doesn't cause the core to expand. Instead, the heat increases the fusion rate, which produces more heat, which increases the fusion rate further. It's a runaway reaction, an unstable, explosive feedback loop. Within seconds, the fusion rate goes from near zero to something like 100 billion times the sun's current total luminosity. 100 billion times for just a few seconds. This event is called the helium flash. And here's the thing that makes it even more mind-blowing. We can't see it. The helium flash happens deep in the core, completely surrounded by the outer layers of the star. By the time any of that energy works its way to the surface, remember that random walk journey light has to take, it's been spread out, absorbed, re-emitted, and distributed throughout the star. The helium flash is one of the most violent events in a single star's life, and it's completely invisible from the outside. The star's surface barely changes. It just quietly rearranges itself. After the helium flash, the degeneracy in the core is broken. The core becomes a normal gas again, and helium fusion settles down into a stable, controlled rate. The star is now on what astronomers call the horizontal branch, a new period of stability, where it fuses helium in the core and hydrogen in the shell around it. But this phase doesn't last nearly as long as the main sequence. Helium fusion is more energy-intensive and proceeds faster. In stars like our sun, this phase lasts maybe 1 billion years or so. And then the helium starts running out too. And the whole cycle, shell ignition, expansion, temperature increase, starts again. The core begins fusing helium into carbon and oxygen. The star expands again into an even larger, brighter, asymptotic grand branch star, pulsing, unstable, blowing off enormous amounts of material from its surface. The star is aging now, really aging.
And what happens next depends, crucially, on its mass. The fork in the road. Mass determines everything. Here's where the story splits. Stars that are roughly less than about 8 times the mass of our Sun, which includes our Sun and the vast majority of stars in the galaxy, will follow one path. Stars that are more than about 8 times the mass of our Sun will follow a completely different path, and the two paths lead to completely different ends. For the lower mass stars, the Sun-like stars, the path leads to something surprisingly beautiful. For the monsters, the path leads to one of the most extreme events in the universe. Let me tell you about the Sun-like stars first, and then I'll tell you about the monsters. The planetary nebula, a star saying goodbye. Okay, our Sun, 7 billion years from now, deep in its asymptotic grand branch phase, huge, red, unstable, pulsating, the outer layers are being blown away more and more aggressively. Over the course of maybe 100,000 years, the Sun, and stars like it, will lose somewhere between 40 and 60% of their total mass, just blown off into space. And this ejected material forms a shell of gas around the dying star, a planetary nebula. I want to pause here because the name planetary nebula is one of the great historical misnomers in all of science. Planetary nebula have absolutely nothing to do with planets. They were named in the 18th century by William Herschel, who looked through his telescope and thought they looked a bit like the disk of a planet. They don't, and they aren't. But the name stuck. A planetary nebula is actually a shell, sometimes several shells, of gas that a dying star has blown off its outer layers. And they are extraordinarily beautiful. Some of the most iconic Hubble images are planetary nebula, the Ring Nebula, the Cat's Eye Nebula, the Helix Nebula, the Butterfly Nebula. Rings and bubbles and intricate structures of glowing gas lit up by ultraviolet radiation from the hot stellar core at the center. Stunning. Anyway, so we've got this red giant, the core is still contracting, getting hotter, and all that helium that's been building up in the center is about to become very relevant.
The iron problem. Why stars cannot escape this. Iron is the end point. Iron is special, uniquely, catastrophically special because of something in its nuclear structure. Every nuclear fusion reaction works because the products are lower in energy than the starting materials. The binding energy, the energy that holds a nucleus together, is higher for the products than the reactants. That released energy is what powers the star. But iron has the highest binding energy per nucleon of any element. What that means is fusing iron into heavier elements doesn't release energy, it requires energy. And splitting iron into lighter elements also requires energy. Iron is at the bottom of the energy valley. It's the most stable nucleus. You cannot fuse it for energy. You cannot split it for energy. It is, energetically, a dead end. So when silicon fusion produces iron and the iron accumulates in the core, nothing happens. No fusion, no energy production, no radiation pressure, just gravity. And now, gravity, with nothing to oppose it, does exactly what it's been trying to do for millions of years. It wins. The core collapse, the fastest thing in astrophysics. When the iron core of a massive star reaches the Chandrasekhar limit, about 1.4 solar masses, electron degeneracy pressure is not enough to hold it up. And something extraordinary happens. The core collapses, but not slowly, not over millions of years like the gradual changes we've been discussing. The core collapses in about 1/4 of a second. The entire core, Earth-sized, more than a solar mass, collapses to a ball about 30 kilometers across in 0.25 seconds. At that speed, the infalling matter reaches a velocity of about 70,000 kilometers per second. That's about 23% of the speed of light. 1/4 second, 23% the speed of light.
And as this happens, something bizarre occurs. The pressure is so extreme that electrons and protons are literally forced together. Electron plus proton equals neutron plus neutrino. The entire core is neutronized, converted from a mix of nuclei and electrons into a ball of neutrons. A neutron star is born. We'll talk about neutron stars in exquisite detail in the next chapter, but here's what that collapsing core does to the rest of the star. The bounce, and then the explosion. As the core collapses, the outer layers of the star, which have been sitting there, supported by the core, start falling inward too. They fall fast, very fast, towards the newly forming neutron star. But the neutron star is incredibly rigid. It's held up by neutron degeneracy pressure, the same principle as electron degeneracy pressure, but for neutrons, and it's much, much stronger. So the infalling outer material hits the neutron star and bounces. The bounce creates a shock wave that propagates outward through the star. And while physicists are still debating the exact mechanism, this is an active area of research, and the models are extremely complex. That shock wave, aided by the almost unimaginable flood of neutrinos pouring out of the neutron star, blows the entire outer star apart. The result is a core collapse supernova, also called a Type II supernova, and the numbers involved are just obscene. The energy released in a supernova is roughly 10 to the 44th joules. To put that number in context, our sun will produce approximately 10 to the 44th joules of energy over its entire 10 billion year lifetime. A supernova releases that much energy in about 10 seconds. 10 seconds. But here's the thing that makes this even more mind-blowing. Only about 1% of that energy is released as light and kinetic energy, the actual explosion. The other 99%? Released as neutrinos. Neutrinos are nearly massless particles that interact almost not at all with normal matter. They can pass through a light year of solid lead without being stopped. And in 10 seconds, a supernova releases more neutrinos than the sun will emit in 10 billion years. That flood of neutrinos is so intense that even though they barely interact with matter, the sheer number of them is enough to push, to help blow the star apart. Even the most antisocial particles in the universe get drafted into the explosion. What a supernova looks like from a distance. Now, here's the perspective shift I want you to have. Imagine you're on a planet in a star system about 100 light-years from a massive star. One night, you look up in the sky, and where before there was nothing visible to the naked eye, suddenly there's a new star, and it's bright, getting brighter. Within a few days, it's brighter than Venus, brighter than the moon, bright enough to cast shadows at night, bright enough to be visible in full daylight. For weeks, this new star blazes in the sky, and then, slowly, over months, it fades. This has actually happened in recorded history. In 1054 AD, Chinese and Arab astronomers recorded a new star, what we now know was a supernova. It was bright enough to be seen in daylight for 23 days. At night, it cast shadows. This supernova created what we now call the Crab Nebula, a beautiful, intricate cloud of expanding gas that the Hubble telescope has photographed in breathtaking detail. And at its center, a pulsar, a rapidly spinning neutron star, the remnant of the star that exploded nearly 1,000 years ago. The most recent supernova visible to the naked eye was supernova 1987A in a galaxy called the Large Magellanic Cloud, a small companion galaxy to the Milky Way. Astronomers detected the neutrino burst from this supernova before the light arrived, because neutrinos were being emitted from deep in the collapsing core, and the light took time to fight its way through the exploding outer layers. For about 3 hours, Earth was bathed in neutrinos from a dying star, and nobody on Earth noticed. Then, the light arrived. 24 particles were detected in total across 3 separate detectors around the world. 24 particles from the incomprehensible flood of 10 to the 58th neutrinos that the supernova produced. And those 24 particles told us that our models of stellar collapse were correct, confirmed the existence of neutron stars, and gave us our first direct observation of a stellar death. 24 particles changed astrophysics.
The supernova's gift, building the periodic table. Here's the thing I want you to hold on to. A supernova doesn't just destroy, it creates. Everything up to iron on the periodic table was made inside stars through the layers of fusion we talked about. Hydrogen and helium from the Big Bang, carbon, nitrogen, oxygen from stellar fusion, silicon, sulfur, calcium from heavier fusion stages. But what about the elements heavier than iron? Gold, silver, platinum, uranium, lead, iodine. Iodine, which your thyroid literally cannot function without. These can't be made by normal stellar fusion. They require a process that only happens in the most extreme environments, like a supernova. In a core-collapsed supernova, there's a brief window where the conditions are right for what's called the R process, rapid neutron capture. Free neutrons in enormous abundance are captured by atomic nuclei in rapid succession. The nuclei absorb neutron after neutron before they can decay, building up into heavier and heavier isotopes. And then those unstable isotopes decay into stable heavy elements. Gold, platinum, silver, all the heavy metals. A supernova, or as we've discovered more recently, the collision of 2 neutron stars, is where the gold in your jewelry was made. The gold in every engagement ring on Earth was forged in the death of a star, or in a cataclysmic neutron-star collision billions of years ago. Every element in the periodic table, every single one, has a stellar origin story. Hydrogen and helium, the Big Bang. Everything up to iron, stellar fusion. Everything heavier than iron, supernovae and neutron star mergers. The periodic table is the story of stellar evolution. Chemistry is literally the legacy of dead stars. The supernova remnant, the echo of an explosion. After the supernova, the outer material of the star, all those enriched heavy element-laden gases, expands outward. It slams into the surrounding interstellar medium at thousands of kilometers per second. The collision creates a shock wave that compresses and heats the gas, causing it to glow. Over thousands of years, the supernova remnant expands, cools, and eventually merges into the general gas of the galaxy. But for those thousands of years, it's one of the most beautiful objects in the sky. The Crab Nebula, which I mentioned earlier, is only about 970 years old, and it's already about 11 light-years across, expanding at about 1,500 kilometers per second. The Veil Nebula, remnant of a supernova about 8,000 years ago, is about 110 light-years across and looks like delicate glowing lace across the sky. Cassiopeia A, one of the brightest radio sources in the sky, is the remnant of a supernova that occurred about 340 years ago, but because of intervening dust, nobody on Earth seems to have seen it at the time. These remnants are beautiful, and they're important because this enriched, shocked gas is the raw material for new stars. The cycle continues. But what about the thing left behind at the center? Because that's where the universe gets really strange. The afterlife, white dwarfs, neutron stars, and black holes. Okay, this is where we go deep. Really deep, because the remnants of stellar death are some of the most extreme, bizarre, mind-bending objects in the known universe, and I want to take the time to do them justice. White dwarfs, a second look. We talked about white dwarfs briefly when discussing sun-like stars, but I want to revisit them now that we have more context. A white dwarf is the exposed core of a dead star. Carbon and oxygen, mostly. In some cases, just helium. In rare cases, oxygen, neon, and magnesium. Compressed to the size of Earth, with the mass of the Sun.
The surface gravity of a white dwarf is about 350,000 times that of Earth's surface gravity. If you somehow stood on the surface, if there was a surface to stand on, which there isn't, you would weigh about 25 million kilograms. Your bones would be compressed to near nothingness. You would, as the physics says, be thoroughly dead. A white dwarf is also genuinely hot when it forms. The surface temperature of a newly formed white dwarf can be 200,000 degrees or more, and it emits enormous amounts of ultraviolet radiation, which is why it lights up the planetary nebula surrounding it so brilliantly. But it's cooling, always cooling. With no fusion to replenish its heat, it's just radiating away the energy it built up over its lifetime, like a coal pulled from the fire, slowly dimming. The most interesting thing about white dwarfs, beyond the physics we've already discussed, is their composition. The carbon and oxygen in a white dwarf isn't just randomly distributed. Under the extreme pressure in the core, carbon and oxygen atoms can crystallize. They can form a crystal lattice. The interior of an old, cooled white dwarf is essentially a giant crystal, a diamond core star. BPM 39093, nicknamed Lucy by astronomers, Lucy from the Beatles song Lucy in the Sky with Diamonds, is a white dwarf about 50 light-years from Earth that is approximately crystallized, a diamond roughly 2,500 miles across. The universe has a flair for the dramatic. Neutron stars, the universe's most extreme objects that still exist. Now let's talk about neutron stars. I've been building to this, because neutron stars are, and I don't say this lightly, the most mind-bending objects in the universe that we know definitely exist. Black holes might be more extreme, but there's a philosophical argument about whether they exist in the same sense. We'll get there. A neutron star is what's left behind after the core collapse of a massive star. The core is compressed so intensely that protons and electrons merge into neutrons, and the result is a ball of neutrons about 20 to 30 kilometers across. That's smaller than most cities. The island of Manhattan is about 22 kilometers long. A neutron star is roughly the size of Manhattan. But it weighs somewhere between 1.4 and 2.3 times the mass of the Sun. Let's make that concrete. Our Sun weighs about 2 times 10 to the 30 kilograms, 2 followed by 30 zeros. A neutron star of 1.4 solar masses compresses that amount of material into a sphere 20 kilometers across. The density of a neutron star is approximately 3.7 times 10 to the 17 kilograms per cubic meter. The density of water is 1,000 kilograms per cubic meter. A neutron star is 370 quadrillion times denser than water. A single teaspoon, just 1 teaspoon of neutron star material would weigh about 1 billion tons on Earth. 1 billion tons in a teaspoon. The surface gravity of a neutron star is roughly 200 billion times Earth's surface gravity. If you somehow dropped a marshmallow onto the surface of a neutron star from a height of 1 meter, it would hit the surface with the energy of a nuclear bomb. A marshmallow. The surface of a neutron star is made of crystallized iron, an actual iron crystal about 1 kilometer thick, harder than anything that could exist on Earth. Below that iron crust, neutron-rich nuclei, becoming increasingly neutron-heavy as you go deeper. And in the innermost core, we genuinely don't know. The densities there are so extreme that normal nuclear physics breaks down. The neutrons might dissolve into a sea of quarks, the fundamental particles that make up protons and neutrons. There might be exotic states of matter that don't have names yet. Strange quark matter, color superconducting quark matter, exotic particles that only exist in particle accelerator experiments for microseconds. A neutron star's core is the most extreme laboratory of physics in the universe, and we can't look directly inside it. We can only infer what's there from the star's observable behavior. Pulsars, the universe's most precise clocks. Here's something incredible about neutron stars. They spin fast. When a massive star collapses to form a neutron star, it conserves angular momentum. Angular momentum is the spinning equivalent of linear momentum.
It's conserved, meaning if you compress a spinning object, it spins faster. It's the same reason an ice skater spins faster when they pull in their arms. The massive star was spinning, maybe slowly, maybe making a full rotation in months or years, but it was enormous, millions of kilometers across. When it collapses to 20 kilometers across, the spin speeds up, dramatically. A newly formed neutron star can complete hundreds of rotations per second. As it spins, its powerful magnetic field, billions or trillions of times stronger than Earth's magnetic field, funnels radiation into beams shooting out from the magnetic poles, like a cosmic lighthouse. And if those beams happen to be aligned so that they sweep past Earth with each rotation, we detect a pulse of radio waves, regular as clockwork, precise as an atomic clock. These objects are called pulsars. The first pulsar was discovered in 1967 by Jocelyn Bell Burnell, then a graduate student, and her supervisor Anthony Hewish. The signal was so regular, so artificial seeming, that for a brief period they actually considered whether it might be an alien transmission. They nicknamed it LGM-1, Little Green Men 1. It wasn't aliens, it was a neutron star. But I love that the universe made something so precise that the first humans to detect it thought it had to be artificial. Pulsars are some of the most precise clocks in the universe. The millisecond pulsars, the fastest spinning ones, are so regular that they rival the best atomic clocks humans have ever built. We actually use arrays of pulsars as a kind of cosmic GPS system, the Pulsar Timing Array, to detect gravitational waves. More on that in a moment. Magnetars, when neutron stars go to the extreme. If neutron stars are extreme, magnetars are what happens when extreme goes further. A magnetar is a neutron star with an exceptionally powerful magnetic field. How powerful? A magnetar's magnetic field is about 10 to the 15 Gauss. Earth's magnetic field is about 0.5 Gauss. A magnetar's field is 2 quadrillion times stronger than Earth's. And this is not an academic distinction. At a distance of 1,000 kilometers from a magnetar, the magnetic field is so intense that it would disrupt the electrons in your atoms. It would destroy the chemistry in your body by literally changing the shape of your atoms. Distance of 1,000 kilometers. The moon is 384,000 kilometers away. A magnetar at the distance of the moon would be fatal. Don't worry. The nearest known magnetar is thousands of light years away, and there are probably only a few dozen in the entire galaxy. But in 2004, a magnetar about 50,000 light years away, called SGR 1806-20, had a flare. A starquake on its surface caused a sudden rearrangement of its magnetic field. The resulting burst of gamma rays and X-rays reached Earth on December 27, 2004, from 50,000 light years away. And it was briefly the brightest thing ever seen in the sky outside our solar system. It ionized Earth's upper atmosphere. It affected the readings of gamma ray detectors around the world and in space. From 50,000 light years away. A hiccup on the surface of a star 470 quadrillion kilometers away physically affected Earth. The universe is very large, and some things in it are very violent, and sometimes those two things conspire to make you feel very small. Neutron star mergers, when two dead stars collide. One more neutron star story before we get to black holes, because this one is special. Sometimes, two neutron stars orbit each other in a binary system, and over millions or billions of years, they spiral closer and closer together, radiating away orbital energy as gravitational waves. Gravitational waves, ripples in space-time itself, predicted by Einstein's general relativity, produced by accelerating masses. For decades, we could only infer gravitational waves indirectly. Then, on September 14, 2015, the LIGO detector detected the first direct gravitational wave signal from the merger of two black holes. This was one of the greatest scientific achievements in history. The Nobel Prize in Physics 2017 was awarded for it. But it was the second major gravitational wave detection that really made my jaw drop. On August 17, 2017, LIGO and its European counterpart Virgo detected a gravitational wave signal. But this one was different. It was longer, more complex.
And 17 seconds after the gravitational wave signal ended, gamma-ray detectors in space detected a short gamma-ray burst from the same direction. And then, optical telescopes pointed at that direction and saw a new, glowing point of light. This was the first multi-messenger astronomy event ever recorded. We were watching the merger of two neutron stars in real time, across every wavelength of the electromagnetic spectrum, and in gravitational waves, and in neutrinos. Two dead stars, spiraling towards each other for millions of years, finally colliding. In the immediate aftermath of the merger, in the fireball of the collision, the R process we talked about earlier was happening in real time. Heavy elements being forged in the nuclear cauldron of two colliding neutron stars. Gold, platinum, uranium, iodine. Astronomers watching the spectrum of this event, called AT 2017 GFO, saw the chemical signatures of freshly synthesized heavy elements. Newly minted gold glowing being scattered across space. In just a few days, this one neutron star merger created somewhere between 3 and 13 Earth masses worth of gold. 3 to 13 Earth masses of gold, created in a stellar collision about 130 million light-years away, detectable from Earth. Black holes, where physics goes to die. Sort of. And now, black holes. I've been deliberately saving this, because black holes require a different kind of mental preparation. They require you to genuinely let go of your everyday intuitions of space and time and matter, because black holes are places where those intuitions break completely. Let's start from the beginning.
What is a black hole? At its most basic level, a black hole is a region of space where gravity is so intense that nothing, not matter, not light, not anything, can escape it. The point of no return, the boundary around a black hole, is called the event horizon. Not a physical surface, not a wall, just a boundary in space. If you cross it, you're not coming back. And because light can't escape either, black holes are, by definition, black. We can't see them directly. We see them by their effects. By the light from material falling into them, by the distortion of space-time around them, by the behavior of stars orbiting near them. How does a black hole form? In the case of stellar mass black holes, the kind formed when massive stars die, the process is basically a continuation of what we described with neutron stars. A massive star's core collapses, but in this case, the core is too massive even for neutron degeneracy pressure to hold it up. There is a maximum mass for a neutron star, roughly 2 to 3 solar masses, depending on the equation of state of ultra-dense matter, which we don't fully understand yet. If the collapsing core exceeds this limit, neutron degeneracy pressure fails, and the collapse continues, past the density of nuclear matter, past the density of quarks, all the way to... we don't actually know. In general relativity, the math says the collapse continues to a singularity, a point of infinite density. But here's the honest truth. Physicists don't believe singularities are physically real. They believe the singularity is a sign that our theories break down, that general relativity, Einstein's theory of gravity, is incomplete, that it needs to be combined with quantum mechanics in a theory of quantum gravity that we don't yet have. What's actually at the center of a black hole? Nobody knows. The singularity is where general relativity puts its hands up and says, "I've taken you as far as I can. Beyond this point, you need a theory we haven't invented yet." The event horizon, the point of no return. Let's talk about the event horizon. The event horizon of a black hole is defined by a surprisingly simple concept. For any massive object, there's something called an escape velocity, the speed you need to achieve to escape its gravity. Earth's escape velocity is about 11 kilometers per second, fast enough and you escape Earth's gravity entirely. For the Sun, it's about 620 kilometers per second. For a black hole, the escape velocity at the event horizon is the speed of light, 300,000 kilometers per second, which means nothing can escape, because nothing can go faster than light.
The size of the event horizon, the Schwarzschild radius, is actually remarkably easy to calculate from the mass of the black hole. For a black hole with the mass of our Sun, the Schwarzschild radius is about 3 kilometers. 3 kilometers. If you compressed the entire Sun into a sphere 3 kilometers across, the mass wouldn't change, but the escape velocity from the surface would equal the speed of light, and it would become a black hole. For Earth, the Schwarzschild radius is about 9 millimeters. A marble. If you compressed all of Earth into a marble, it would become a black hole. What happens when you fall in? This is probably the most frequently asked question about black holes, and the answer is genuinely strange. Let's say you're an astronaut falling into a stellar mass black hole. As you approach the event horizon, the tidal forces become extreme. Tidal forces arise because gravity is stronger on the side you're closer to the black hole than on the side farther away. For a small black hole, this difference is so extreme that it would literally stretch you head to toe while squeezing you side to side. Physicists have a wonderful technical term for this: spaghettification. You would be stretched like spaghetti. From your own perspective, if it happened instantly enough that you were somehow still conscious, you would see the universe above you become compressed into a bright ring. The light from the entire rest of the universe, blue-shifted, compressed into a shrinking window above you. And from a distant observer's perspective, they would never see you cross the event horizon. Because of time dilation, predicted by general relativity, time runs slower in a stronger gravitational field. From the distant observer's perspective, as you approach the event horizon, you appear to slow down. Your light becomes increasingly redshifted, stretched toward longer wavelengths, until it becomes too faint to detect. You appear to freeze at the event horizon, slowly fading, never quite crossing. From your perspective, you cross the horizon in finite time. From outside, apparently, you never reach it. Both are equally valid, consistent descriptions. General relativity is strange. Now, there are supermassive black holes, which have much gentler tidal forces at the event horizon because they're so enormous. For a supermassive black hole with 1 billion solar masses, the tidal forces at the event horizon are actually quite gentle. You might cross the event horizon without feeling anything unusual. You wouldn't even know. You'd just be inside, unable to leave, falling toward the singularity with no way to communicate to anyone outside what you're experiencing. Types of black holes. There are broadly 4 types of black holes. Stellar mass black holes, formed from collapsing massive stars, masses of 3 to maybe 100 solar masses, scattered throughout galaxies. Intermediate mass black holes, somewhere between 100 and 100,000 solar masses. We have good evidence for these, but they're harder to find. Supermassive black holes, millions to billions of solar masses, found at the centers of almost every large galaxy, including ours. Primordial black holes, hypothetical black holes formed in the very early universe from density fluctuations, not from dying stars. Some physicists think primordial black holes of certain masses could be a component of dark matter. This is unconfirmed. The supermassive black hole at the center of our galaxy, called Sagittarius A*, has a mass of about 4 million solar masses. In 2022, the Event Horizon collaboration released the first image of Sagittarius A*, and it looked exactly as Einstein's theory predicted: a bright ring of glowing gas around a dark shadow, the shadow of the event horizon. The actual photograph of a black hole. A photograph of a place where physics breaks down. One of the most extraordinary images in the history of science. Hawking radiation. Black holes aren't forever. One more black hole thing, because I'd be remiss if I didn't mention it. In 1974, Stephen Hawking showed, using a combination of quantum mechanics and general relativity, that black holes are actually perfectly black. They radiate very, very slowly. The mechanism involves virtual particle-antiparticle pairs that are constantly being created and annihilated at the quantum level everywhere in space. Near the event horizon, sometimes one of these virtual particles falls in while the other escapes. The escaping particle carries energy away from the black hole. The black hole loses mass. very, very slowly. For a stellar mass black hole, the Hawking radiation temperature is so cold, billionths of a degree above absolute zero, that the radiation is completely undetectable against the background of the universe. And the black hole would take longer than the current age of the universe to lose any appreciable mass this way. But eventually, in the incomprehensibly distant future, after the last stars have died and the universe has gone dark, black holes will slowly evaporate, growing smaller and hotter as they do. And in the very last moments, as a black hole completely evaporates, it will release a burst of high-energy radiation, a final flash, a remnant's last goodbye. And then, nothing. Not even a black hole. Just radiation spreading out into the cooling darkness of an ancient universe.
The dark night sky, Olber's paradox, and what it tells us. I want to end this chapter with something that sounds simple but is deeply profound. Why is the night sky dark? I mean, if the universe is infinite and full of stars, shouldn't there be a star in every direction you look? Shouldn't the night sky be as bright as the surface of a star? This puzzle was pondered by astronomers for centuries. It's called Olber's paradox, and the answer is beautiful. The night sky is dark because the universe is not infinitely old. It's only 13.8 billion years old, and light has a finite speed. So the light from stars more than 13.8 billion light-years away hasn't reached us yet. We can only see the light from stars that formed close enough, long enough ago, for their light to have made the journey. Beyond that distance, the cosmic horizon, there's light, there are stars, there is structure, but we can't see it, and will never see it. Because the universe is also expanding. Stars beyond a certain distance are moving away from us faster than their light can reach us. They're beyond our causal horizon forever. The darkness of the night sky isn't emptiness, it's the limit of what a young, finite, expanding universe can show us. Every dark patch of sky is full of stars we'll never see. Galaxies full of suns, full of planets, full of, maybe, life. Just out of reach. The universe is vaster than we can see, and it has been going on longer than we can truly comprehend. And we are here, in this one corner of it, for this one moment, looking up, wondering. The future. What happens to stars from here? I want to close by talking about the future, not the future in terms of years or decades or even centuries, the far future, the cosmic future. Because understanding where stars are going and where the universe is going is just as profound as understanding where they came from. The stellar main sequence today. Right now, in this moment, across the Milky Way galaxy, there are somewhere between 100 and 400 billion stars in various stages of their lives. Some are just being born, protostars igniting in stellar nurseries, beginning their billions of years of hydrogen fusion. Some are middle-aged, quietly stable, like our sun. Some are red giants, aging, expanding. Some are dying in planetary nebulae right now, forming white dwarfs. Some are exploding in supernovae right now, and we just haven't seen the light yet because they're thousands of light-years away. The galaxy is alive with stellar activity at every moment. And beyond the Milky Way, the observable universe contains somewhere around 2 trillion galaxies. 2 trillion, each containing billions to hundreds of billions of stars. The total number of stars in the observable universe is estimated at around 10 to the 24. 1 septillion, a 1 followed by 24 zeros. Each one on its own journey, its own life cycle, its own story. But here's the long view. The universe's ability to form new stars is not unlimited. Stars need hydrogen. Hydrogen is finite. Over trillions of years, much longer than the current age of the universe, the hydrogen supply in galaxies will slowly be used up. New star formation will slow, eventually stop. The last stars will be red dwarfs, those small, slow-burning, ultra-efficient stars that live for trillions of years.
the last red dwarf in the Milky Way will die, slowly cooling into a black dwarf, roughly 100 trillion years from now. 100 trillion years. For comparison, the current age of the universe is about 13.8 billion years. 100 trillion is more than 7,000 times that. After the last stars die, the universe enters what cosmologists call the degenerate era. Galaxies dark except for the faint glow of white dwarfs, neutron stars, and black holes. Occasionally, if two white dwarfs collide, a brief nova, or a Type 1a supernova, one last flash of violence in an otherwise dark universe. Eventually, over timescales of 10 to the 36 years or more, even protons may decay, if current theories about proton decay are correct. All ordinary matter dissolves into radiation and leptons. The white dwarfs and neutron stars evaporate. Only black holes remain, and they, as we discussed, slowly evaporate via Hawking radiation. The last black holes will evaporate after roughly 10 to the 100 years, a Google. After that, an expanding, cooling, dark universe. Photons and neutrinos and electrons and positrons spread impossibly thin across an incomprehensibly vast space. Thermodynamic equilibrium. Heat death. The end of the story. Or maybe not. Maybe there are processes at those timescales that we can't predict. Maybe the universe is cyclical. Maybe there are fluctuations, quantum fluctuations, that given enough time spontaneously organize into new complexity. We don't know. We genuinely don't know. And I find that oddly beautiful, not frightening, because the story, right now, in 2025, is still very much in progress. We are in the bright, star-filled, life-filled chapter of the universe's existence. We are here when there is light, when there are stars to look at, when there is a night sky to wonder about. Enjoy it.
The plot twist. You are stardust. Okay, we've been on a journey. We started with a cold, dark cloud of gas. We watched a star form, ignite, settle into stability, live for billions of years, quietly, brilliantly, fusing hydrogen into helium. We watched it age, expand, glow red. We watched it die, some quietly, blowing off their outer layers in a beautiful planetary nebula, leaving behind a crystalline white dwarf. Others violently, in the most energetic explosions since the Big Bang, scattering the contents of their cores across light years of space. We met neutron stars, city-sized balls of neutrons spinning hundreds of times per second with magnetic fields that would kill you from the distance of the moon. We met black holes, regions of space-time where physics breaks. And now I want to bring it home, because all of this isn't just abstract astrophysics, it's personal. The cosmic connection. You are downstream from stars. Let me walk you through the specific atoms in your body. Your body is about 65% oxygen by mass, 18% carbon, 10% hydrogen, 3% nitrogen, and then iron, calcium, phosphorus, potassium, sodium, and a dozen other elements in smaller amounts. Hydrogen, made in the Big Bang, 13.8 billion years ago. Oxygen, made in the cores of stars through helium fusion, scattered by stellar winds and supernovae. Carbon, same origin, made in the helium fusion layer of dying stars. Nitrogen, made in stellar fusion and scattered in supernovae. Iron, made in the silicon fusion layer of massive stars, the last fuel they burned before collapse. Calcium, made in oxygen-burning and silicon-burning stages of massive stars. Phosphorus, same. Every one of these atoms has a history that predates our solar system. The oxygen in your lungs right now, it was fused from helium inside a star that lived and died before our sun was born.
The carbon in your DNA, every C in the sequence, was forged inside a stellar core, scattered in a supernova or stellar wind, and eventually incorporated into the gas cloud that became our solar system. The iron in your blood, specifically the iron in the hemoglobin that carries oxygen to your cells, that iron was made in the final hours of a massive star's life, in the frantic silicon burning stage that lasted barely a day. And when that star exploded, that iron was scattered into space. It drifted. It was incorporated into our solar system when it formed 4.6 billion years ago. It settled into the Earth. Over billions of years, through geology and chemistry, and eventually biology, it was incorporated into living things, and eventually, after an unimaginably long chain of events, into you. The iron in your blood remembers, if we can use that word, a star. The Carl Sagan's quote, the most true cliché. There's a quote that gets said so often that it's almost become a cliché. We are made of star stuff. Carl Sagan said it. And it's said so often now that it kind of slides off people's minds. But I want you to really hear it, not as a poetic metaphor, not as a nice sentiment, as a literal, chemical, physical fact. You are not metaphorically made of stars. You are actually, in the most concrete and direct sense, made of material that was forged inside dead stars. The matter you're made of has already survived a supernova. You are, in the most literal sense, a descendant of stellar violence. You are the universe's way of looking at itself. The atoms that were once inside a star are now arranged into a pattern complex enough to be conscious, to ask questions, to wonder about the universe. The universe made you out of itself, destroyed some of its own stars to do it, scattered their contents across space over billions of years. And here you are, thinking about it. The overview effect, from astronauts to you. There's something called the overview effect. When astronauts see Earth from space, from orbit, or from the moon, many of them describe a profound psychological shift. They describe seeing the planet as small, fragile, unified, no borders visible, just this thin film of atmosphere over an impossibly beautiful sphere. And they describe a sense of connection to everything on it. The overview effect is a well-documented psychological phenomenon. Multiple astronauts have described it independently with strikingly similar language. It changes people. I think learning about the life of stars is its own kind of overview effect, not by going somewhere and looking back, but by understanding deeply where the matter you're made of has been. You carry in your body atoms that have been inside the cores of stars, atoms that have survived stellar winds and supernovae, atoms that have drifted through interstellar space for millions of years, atoms that were incorporated into the first living cells on Earth and have been passed from organism to organism in an unbroken chain for billions of years. You are the latest temporary arrangement of ancient stardust. And at some point in the far future, billions of years from now, those atoms will be scattered again. When the sun dies, when the Earth is gone, they'll drift back into space, maybe get incorporated into a new star, maybe into a new planet, maybe into a new kind of life that we can't imagine. The atoms don't end with you, they just move on. The time scales, putting it all together. I want to do something here. I want to lay out the full timeline of everything we've discussed, because I think when you see it all together, something clicks. The universe is 13.8 billion years old. In the first few minutes after the Big Bang, hydrogen and helium were made, some lithium, that's it. The entire periodic table above helium was zero. About 200 to 400 million years after the Big Bang, the first stars formed, massive hydrogen and helium behemoths. They lived fast and died young, exploding in supernovae and seeding the universe with the first heavy elements. We call these population 3 stars. None of them exist today. The next generation of stars, population 2, formed from gas enriched by those first deaths. They're still helium and hydrogen dominated, but with traces of heavier elements. Some of them still exist today in the halo of our galaxy, ancient, metal-poor stars, some nearly as old as the universe itself. The current generation, population 1 stars like our Sun, formed from even more enriched gas, with enough heavy elements for rocky planets to form around them, for chemistry to be complex enough for life. Our Sun formed 4.6 billion years ago. Earth formed 4.5 billion years ago. The first life on Earth appeared roughly 3.8 to 4 billion years ago. Complex multicellular life, about 600 million years ago. Dinosaurs, about 230 million years ago. Humans, about 300,000 years ago. You, reading this, right now. The entire history of humanity, all of recorded civilization, all of history, all of science and art and music and war and love, is a tiny sliver at the very end of a story that started with a Big Bang 13.8 billion years ago. And the story isn't over. Our Sun has about 5 billion years left on the main sequence. After it dies, the atoms it's made of, and the atoms you're made of, will continue, incorporated into new clouds of gas, into new stars, into new planets. The universe's story is only about a third of the way through in terms of main sequence stellar evolution. There are generations of stars yet to live and die, planets yet to form, chemistry yet to emerge, life yet to arise, maybe, hopefully. We are not the end of the story. We are a chapter.
The big picture. What this all means. Let me leave you with this. We live in a universe that, as far as we can tell, had no particular obligation to be interesting. It could have been a universe of pure hydrogen, with no way to form complex structures. It could have been a universe where the constants of physics were slightly different, where stars couldn't form, or couldn't last long enough, or couldn't make heavy elements. It could have been a universe where the Big Bang produced just radiation and nothing condensed into matter. Instead, we got this. A universe that made stars. Stars that lived for billions of years, quietly making the elements. Stars that died, scattering those elements into space. Gas clouds that condensed again, forming new stars, and around them, planets. Planets where chemistry happened, where the right elements, in the right proportions, dissolved in the right liquids, under the right conditions, made life. Life that evolved over billions of years into creatures complex enough to look up, to wonder, to build telescopes, to take photographs of black holes 55 million light-years away, to sit here watching a video about how stars work. We are, as far as we know, the only part of the universe that is aware of the universe. The only part asking these questions. The universe cannot observe itself except through us. And every time you look up at the night sky and see a star and think, I know what that is. I know what it's doing. I know where it came from and where it's going. That is the universe knowing something about itself. Through you. Made of dead stars, looking up at living ones. I think that's the most extraordinary thing I know. Okay, take a breath. That was a lot. A beautiful, mind-bending lot. We went from a cold cloud of gas in the darkness all the way to the heat death of the universe, with about 1 billion stops along the way. And if there's one thing I want you to take from all of this, one feeling I want you to carry with you the next time you step outside on a clear night and look up, it's this. Every single star you see is a story. A story of birth and balance and fuel and fire. A story that, in many cases, ended before humans existed. The light you're seeing might be from a star that is already dead, already gone through everything we talked about today. You're watching the light from a ghost. And the atoms in your body have already been through some of those stories. They've been in stellar cores. They've been scattered in supernovae. They've drifted through space. They've been you.
And they'll keep going long after you're done with them. You're not separate from the universe. You're part of it. You're made of it. And I think that's worth sitting with. If you made it this far, genuinely, thank you. This is the kind of video I make because I can't stop thinking about this stuff, and I need someone to talk about it with. So here's what I want you to do. Drop a comment and tell me which part hit you hardest. Was it the helium flash? The neutron star? The idea that the gold in your jewelry was made in a stellar collision? Or was it something smaller, some detail that just landed in a weird, wonderful way? I read every single comment, every one. And if you want more of this kind of deep dive, the real, unfiltered, late night, wait, what even is the universe kind of content, subscribe and hit the bell, because we've barely started. Next video, we're going to talk about the Big Bang, what actually happened in the first second of the universe. And I promise you, some of it is going to make today's video look calm. I'll see you there.